So far, we've talked about the concepts of a spanning set and a linearly independent set. We're going to combine these two. Most of you have taken a physics class, and when you work on problems in 2D, you often use these vectors, I and j, to represent every other vector. But in some problems, for example, when you're working on an inclined plane, it's more convenient for you to build a coordinate system that's aligned with the plane. What we're doing is using a new set of vectors because it's more convenient for us. Does this always work? When can I do this? Are there any limitations? And are there other options? So what we're going to do today is we are going to generalize this so that we can come up with a definition, a starting point, so that we can answer these questions. We start with our definition. A basis is a set of vectors v1 through to vn that live in Rn, that is linearly independent and spans Rn. Now this word basis kind of has an English meaning. Basis means foundation. This is what I'm going to call a master set of vectors that can be used to form all other vectors in Rn. And to try to really illustrate to you why a basis is useful, we are going to put these vectors as the columns of some matrix A. Our set goes from v1 through to vn, and that matches Rn. So we're going to put this into the columns of a matrix. Each one of these vectors, vi, lives in Rn, so there are n entries. That means our matrix is n by n. By definition, the columns of A span Rn. That's what part of the definition of a basis is. And if the columns of A span Rn, that means there has to be a pivot in every one of the rows. By definition, the columns of A are linearly independent. That means there has to be a pivot in all of the columns. Now, since A is square, that means there's a pivot in every row, and there's a pivot in every column, and eventually A will be reducible to the identity matrix, and so that means this A is invertible. A basis really does combine all of those ideas that we are talking about before. Span is the idea of being able to build vectors through linear combination. Independence is this concept of the vectors being different enough. And we are putting them together. We're taking the best of both worlds. When you have a basis, you can build all of your vectors, every one of these vectors in Rn, by a linear combination. So it's possible to construct them by taking some linear combination of all of those vectors. You have just the right number of these basis vectors. If you had fewer of them, you wouldn't have a pivot in every row, and they wouldn't span Rn. And if you had more of them, then they would be linearly dependent. If you had more than n of them, you wouldn't be able to have an independent set. The real advantage of this is that there is always going to be a unique solution to any AX equals B. The matrix has columns that span Rn and that are linearly independent. Any vector has a unique representation in terms of a basis. So there are a lot of ideas here. First technique that we want to do is, number one, be able to identify whether a set of vectors is a basis for a given space. If I give you this basis beta, we're always going to refer to it in terms of a set. We're going to ask the question, is this a basis for R2? Always put it into a matrix. Take this as the columns of your matrix, and you can very clearly see we have a pivot in all of our rows and all of our columns. That means this matrix is invertible, and that means that the columns are a basis for R2. Very, very simple. If I give you this other set, which we've all seen before, we will do the same trick. We'll call this set E. We'll put this into a matrix. You will immediately be able to see, yes, there's a pivot in every row, so the set will span. There's a pivot in every column, so the set will be independent. And this set E is a basis for R3. This is what we call the standard basis for R3. Sometimes in physics, we like to call them I, J, and K. In math, we like to call them E1, E2, E3, because it allows us to generalize. We could have the standard basis for Rn. It's very simply formed. E1 would just be the vector with 1 in the first component and zeros elsewhere, and En would be very similar. So this would be the standard basis for Rn. you'll notice that these vectors that I chose weren't really special. They were only special in the sense that they just had to be different enough and there had to be enough of them. So here's a really important realization. There are infinitely many different bases for Rn. You can choose any set that spans and is independent. What is common between all of the bases is that the number of vectors in the basis is always the same. And this number of vectors, we're going to make a definition. We are going to say that the dimension of Rn is the number of vectors in any basis of Rn. And in this particular case, the dimension of Rn is always going to be n. And this is why we call it n-dimensional space, because we need n different vectors to form a basis of Rn. So if there are infinitely many of them, which one do we use? And the answer is always the most convenient one. Most convenient depends on your problem. You might have certain problems like the inclined plane where it's better for you to be on an angle, and some problems where you don't. Now, I've shown you examples of things that are bases. I'm going to show you an example now very quickly of some things that are not bases. If I were to put this as the columns of a matrix, there's only one pivot. This set B, this will not be a basis for R2 because there's not a pivot in every row and there's not a pivot in every column. This first vector B1 and this second vector B2. B2 is just twice of B1. And in terms of a picture, this set B would just create a line. It could not create all of R2. If I were to give you this set of vectors, these two vectors are not multiples, so you could immediately tell that they are linearly independent. If I were to put them into a matrix, and I'll get to something like this, there are two pivots, and I can only hope to have two pivots here because I have a 3x2 matrix. So the columns are linearly independent, but they do not span R3. So in fact, what their span is, the span of this set of vectors is a plane in R3. So we'll say that B is a basis for the plane. And in chapter 3.5, we're going to talk about having a basis for objects like this. So now that we've got the definition of basis, what we're going to do is use it to talk about changing between different bases.